Okay, so let's continue. Again, I remind you that I'm not morning person, so if you don't ask questions, I will fall asleep. So interrupt me, ask questions, and see how far we go. I prepared many slides. I'm sure we'll not go to the end, but let's see how far we can go. Anyway, let's start. So let me remind you very quickly, lecture 1, this already happened yesterday. We discussed superconductivity from repulsion and general principle, how one can get attractive interaction from nominally repulsive one. Hint, these are game of words. You take interaction, which is nominally repulsive, but generally screened interaction by special reasons may have and almost always have at least one attractive component. In isotropic systems, there is a theorem that components with large odd angular momentum are always attractive, so there is definitely superconductivity, even if interaction is purely electron-electron one. Here's what I will do today. I will finish what I was supposed to do yesterday, but there was definitely not enough time to do it, and we'll discuss issue about superconductivity versus competing orders. What happens if there are other orders besides superconducting, and how superconductivity competes when the same interactions wants to produce, say, magnetism and superconductivity, or charge order and superconductivity. So this will be part of the story which goes under umbrella of normalization group. And then we'll discuss what was original subject of lecture 2, namely superconductivity near quantum critical point, and this is sort of modern subject. And the key part that I will be talking about will be superconductivity against non-Fermi liquid. You will see that there are another competition. One competition is superconductivity versus competing orders. Another is superconductivity also compete with non-Fermi liquids. They don't like each other, and they try to avoid each other. So again, let me repeat that main result of previous lecture was the story that modern superconductivity in lattice system, in a zero-order approximation, when you are not interested in numbers, what's the value of TC, and even not interested in details how to get it, is only interested in the issue how to get attraction, then this is the story. So basically what happens, you can start with the system with bare repulsion, think about Hubbard repulsion U, but screening by other fermions makes interaction like momentum dependent. Remember, all our game was that interaction at large momentum transfer becomes larger than interaction at small momentum transfer, and because of this, one partial component of interaction will become attractive. For cuprates, it's D wave. For iron-based materials, it's S plus minus, again, sign changing gap, but between different pockets. And fancy story about doped graphene, it gives you D plus ID superconductivity. Very quickly, let me remind you that that one of the models that we considered was a model. I need to get rid of this. Just give me a second. Okay. Basically, let's go back. One of the models we considered was the model for iron-based superconductors. So this model with hole and electron pockets. And if we consider simplest model, we consider one hole pocket and one electron pocket. I want to get rid of this if I can. Don't know how to do it anyway. We consider the simplest model of one hole and one electron pocket. Two interactions. One interaction is within pocket, another interaction between pockets. We call it G1 and G2. One is inter-pocket interaction. Another is intra-pocket interaction. And the story went that we have two coupling constants. One was definitely repulsive. This is the sum of these two guys. Another one was the difference between two interactions. For Hubbard case, when original interaction is just a constant in momentum space and doesn't care whether it's small momentum transfer or large momentum transfer, this was 0. You go to second order and doing calculation a little bit more fancy than what I showed here. But anyway, what you get to second order is that interaction which you call G2 exceeds interaction which is called G1. You get it to second order almost instantly. And once you get it, then this component becomes negative, means attraction, and then you can only ask the question, what is the consequence? The consequence will be a pair state in which you change the gas sign of the gap or phase of the gap between these two pockets. This will plus minus superconductivity. Very simple result, which doesn't require anything besides solving BCS equations. But this is the beginning of today's lecture. The story is, of course, too good to be true. And the reason it's too good to be true is that you start with Hubbard interaction, which in some cases is okay, and for some system you can more or less rigorously justify that this is good approximation. But let's think about generic case in some sense, in a more general sense. If I asked a simple question, which interaction is larger? You take screen Coulomb interaction. There is one interaction that's small momentum transfer, another interaction that's large momentum transfer. Which one is larger? Take unscreened Coulomb interaction. It goes as 1 over q squared, right? It depends on in what dimension you are. Which one is larger? 1 over q. Of course, the interaction of small momentum transfer is larger, right? You do screening, but you don't expect that things will go inverse. So generally, you start not with the situation when these two guys are equal. If they are equal, then you can go to second order, and on top of 0, you can get negative result, which would be great because it will tell you that there is attraction. But in reality, you start with the case when this guy is larger than this one. So this lambda is positive. And then you can say, forget about perturbation theory, because perturbation theory is something small correction to what you start with. As a result, if lambda was originally positive, then perturbation theory can make it less positive. But you need perturbation theory to exceed certain threshold in order to change the sign of interaction. And this is not what perturbation theory used to be, because it used to be small correction to initial state, right? And therefore, we have real problem, because it's nice to talk in terms of adding something to 0, this one thing. But in reality, we need to add something to positive number. And then perturbation theory is in trouble, which is exactly what I said. And so there are two ways to go from here. Both are not completely exact. As usual, you go away from perturbation theory. You don't expect that you will get exact results. But each approach has its own pluses. Minuses are obvious, but they're pluses. So one is to say, forget about perturbation theory. I want to start with experiment, so experiment will motivate me, and then I will use with some phenomenology, and on top of phenomenology, I will do some reliable calculations. This is basically approach that said, okay, let's look at phase diagram of all these materials, and notice that in most cases, another order state is nearby, most likely magnetism. Then you can say, let's consider a system close to magnetic instability, when almost certainly interaction with large momentum transfer is enhanced simply by virtue of being close to instability with large momentum. Then you can start with phenomenology and consider what happens with superconductivity, what we call close to quantum critical point. And the word quantum critical point simply means that the system is close to an instability at 0 temperature. This will be the second part of this lecture. Alternative is, let's keep interactions weak. Let's not assume that interaction grows up to make Fermi system unstable towards some time of order, but let's try to extend perturbation theory to see whether we can rigorously go beyond second order. Because so far, lecture 1, besides that, again, let me repeat, Kohn-Lattinger analysis by itself was not second order. It was rigorous analysis, but valid for isotropic system and only large values of angular momentum. You go to lattice system, we cannot do anything besides perturbation theory. So the idea is to see whether we can go beyond perturbation theory and find out some finite correction to initially repulsive interaction. So this is what goes under normalization group analysis. This is what we will do now. And just want to quickly list incomplete list of people who are working on this stuff. There is analytical parquet RG, there is a numerical functional RG, there are a number of different approaches. But the physics is this one. So first of all, what's the story? Again, I will play the game with the same interaction. Remember, we need to get interaction which is called G2 to be larger than interaction which is called G1. And G2 is interaction with large momentum transfer. G1 is interaction with small momentum transfer. The question is how to do it. If we look at what are we talking about when we say interaction, terms in the Hamiltonian. Generally, when we write Hamiltonian of lattice system. So which means that basically we are talking about interaction on a scale of bandwidth, of the scale on which interaction have a dispersion. And if we ask what we need for superconductivity, we actually need interaction at much smaller scale, where the largest energy is roughly Fermi energy. There are cases, and Nandini was giving a talk yesterday about situation when Fermi energy is the smallest energy scale, and there is another scale, basically like the bifrequency, which is sitting somewhere here. Still, in any case, it's much smaller than the scale of bandwidth. And if you look at pnictides as a practical example, then roughly bandwidth is few electron volts. Fermi energy is 100 MeV or even smaller. And of course, you cannot work in all this range. So where you stop working with what's called low energy physics is, of course, questionable. But the fact that you have a wide range here gives you a hope that there is plenty of space to work with. What I mean by plenty of space to work with. This is where you define terms in the Hamiltonian. This is your bare interaction. This is what you need. You need interaction at this scale. So what happens? When you want to know what happens with the physics here, you need to integrate out contributions from Fermions in all this range. When you integrate these contributions out, then they change your interactions. So this is what physicists are using to say by the word interaction flow when you go from high energies to low energies. It practices means that if you want to focus on the system here and only know what happens at energies below the scale, you basically need to take all Fermions with energies above the scale and integrate out their contribution to interaction. So renormalize interaction by including all renormalization coming from high energies. And generally, interaction in all channels change. There is one change of interaction in the pairing channel. This is what we are interested in. But if you ask what happens with the interactions that give rise to, say, density wave, spin density wave, or charge density wave, this interaction is what's called particle Hall channel, because density wave parameter is C dagger C, not C dagger C dagger. They also flow. So all interactions flow when you go from high energies to low energies. The question is how. And in this respect, iron pnictides example is a very good example to show what's going on. Because previously, we explored one part of pnictide story, but we didn't explore the other. Remember, pnictide story was that you have small pockets. Some of them, the one in the middle is hole-like dispersion. The one at the corner is electron-like dispersion. We didn't explore this before. We just said interactions G1, G2, but we didn't say what's important that one pocket is hole pocket, another is electron pocket. Now we're trying to explore this. And we explore two-dimensionality as well. Systems are to large extent two-dimensional in the sense that hopping between layers is very small. Yes?
So in your RG, when you do the effective flow, you are assuming some form for the flow. I mean, you're assuming that there are certain kinds of interactions that survive when you integrate out the high energy scale. So you can't get any more exotic multi-particle exchanges or something like that in your theory. You're assuming some two-body form survives all the way to low energy.
No, what you assume is this. You assume that, maybe I will come to this and then I will talk about this a little bit more detail, but you start with 4 Fermion interaction, right? And at this stage, you just ask a question, how these 4 Fermion interactions renormalize. What you are asking is, can you get condensates which are formed, say, not out of 2 particles, but out of 4 particles. This is a different story. Although we're not talking about this part of the story. Yes, the story with pneumatic order in iron-based material. There is one approach to pneumatic order which tells you that pneumatic is a precursor to spin density wave. Then pneumatic order parameter by itself will be constructed out of 4 fermions, not 2 fermions. Then you can use these couplings and construct order parameter which is 4 fermion object. This is a separate line of research. Okay. Okay, let's go. Why is this important? Particle Hall. First of all, why 2D is important? Let's look at particle-particle channel. What means particle-particle? The errors are in the same direction. You create 2 particles, right? We all know that in a particle-particle channel, there is a Cooper instability, right? That's not what we're talking about. We're at energies larger than Fermi energy. So we're not talking about Cooper instability. Cooper instability comes from energy smaller than Fermi energy. Why particle-particle channel is interesting? Because if we are in 2 dimensions and we calculate particle-particle susceptibility of free particles without chemical potential, we're at energies larger than chemical potential. If we are in 2 dimensions, we get logarithm, simply because dispersion is k-square. If it's not k-square, it's a different story, but I cannot talk about all stories possible here. So let's assume that dispersion is simple k-square over 2m. Then we get logarithmical normalization. Okay, let's take it. Let's look at particle Hall channel. Now we play the game Hall and electron type. We calculate this Hall dispersion, this electron dispersion. We calculate particle Hall bubble, but now at momentum transfer that connects these 2 Fermi surfaces. We again get logarithm. Logarithm because of frequencies are the same, but sign of dispersion is different. Do it yourself, you will find it. So there is logarithm here, logarithm there. Why is this important? Because logarithm is a blessing. If you have logarithm in perturbation theory, then wonderful. We know then that we can go beyond second order in perturbation theory. The reason is that we have coupling, and with perturbation theory assumes that coupling is weak. But we can sum up terms not only in powers of coupling, but in terms of powers of coupling times this big logarithm. Logarithm can be made as big as we want if we lower the temperature. So the art then is to say, look, I don't want to include terms in higher orders in small parameter, but I want to include terms in higher orders in parameter times logarithm. And you all know this. It's called Bcs theory of superconductivity. In Bcs theory of superconductivity, what you do, you go below Fermi energy, and let me put Fermi energy as the upper cutoff, and you do summation of these logarithmical terms. That's called Cooper summation of Cooper ladders. And you do get, of course, the result that your effective coupling goes like this. It has denominator. And if G is negative, means attraction, then there is a scale, exponentially small scale, at which your coupling blows up. What means your coupling blows up? Which means that you do initial perturbation, and susceptibility becomes infinite. So you spontaneously break a symmetry and create superconducting order. Again, how you get it? By summing up logarithms. This is what Cooper problem is. You can, and this will be important for the next line of reasoning, this is original way how this was all done, by summing up logarithmical terms. In a slightly more modern version, you can write exactly the same by writing what's called renormalization group equation and asking how the coupling flows. Now it's this BCS problem, so it flows below Fermi energy. This was the story about previous slide, was the story about flow above Fermi energy. But if you look here, you'll find that to get exactly the same result, all I have to do is to write differential equation, dg over d logarithm is equal to minus g squared. If I solve this equation, then I find exactly the same result as this one. So the idea here is that basically you can either sum up logarithms or write down differential equation, you will get exactly the same result. And there is a pretty straightforward procedure how to derive these differential equations. So what I want to do, I want to do exactly the same, but now I have two channels. Again, let me repeat why it's important that to have two channels. Because if I have only particle-particle channel, and you will see it on the next slide, I have repulsive interaction. I cannot get attraction out of purely repulsive interaction. So in any way, I will not be able to do anything. The hope is that there is another channel, which is also logarithmical, and it will give me right push. It will change the story. So let's see whether it's possible or not. What we'll have to do? We have to introduce all relevant couplings, all relevant interaction between fermions. Two of them you already know. Dashed line and solid line here are just fermions close to hole pocket or close to electron pocket. And two of this interaction is our G1 and G2, which I repeated already today 10 times. Interaction within pocket or pairing interaction between pockets. Pairing means, look at these lines. Two lines coming in, two lines goes out. So I create two particles or I create two holes. This is exactly what pairing order parameter C dagger tells me about. But I also have to include interactions which contains momentum transfer between hole pocket and electron pocket. This is what will give me, if developed, order in a particle hole channel, if corresponding interaction is of proper sign. These are two such interactions. One is called forward scattering, another is called backward scattering. But these are from different worlds. These are interactions which you normally don't include into consideration when you solve for superconductivity. Why I included them? Because this interaction will grow up, will change, not grow up, will change logarithmically. And this interaction will change logarithmically between bandwidths, where I defined it, and scale of a Fermi energy where I need it. So my goal is to ask the question, what we get at the scale of Fermi energy when we can start solving Cooper problem. And for this, since I know there are two channels in which interaction flow logarithmically, I can derive a set of RG equations. For this case, it's pretty straightforward, although the equation looks ugly, but it really takes minutes, literally minutes, to derive these equations. I will show you another example when it takes a little bit more than minutes to derive equations. But this equation you can derive rather quickly. And you see all couplings flow. There's a derivative with respect to log, and you know how to read this derivative. It means that perturbation theory contains logarithms. And this equation includes only logarithmical corrections, but do not include regular corrections to higher power of the coupling. Which means, yes, we still assume that we're at weak coupling, and our couplings grow, but they are regionally small. And we expect that something will happen to them while they remain small, because when they're not small, I cannot do it. Then I have to stop perturbation theory. Let's go back one step and say, okay, why we need other channels? Let's get rid of them. These are other channels, right? Let's get rid of these guys. Let's assume that G4 and G3 are just 0. I go back to these two equations, right? We all know how to solve this simple set of two differential equations. Basically, they split into two independent equations for G1 plus G2 and G1 minus G2. Each one is simple differential equation. You solve it, this is the result you get. So this is nothing but solution of these equations. G1 and G2 here are bare values. I try to separate between running variables, which depend on the coupling L, which are here in this equation. All G's in this equation are running variables. What I put here, G1 and G2, are bare values, the ones that you have at the scale of the bandwidths. So dependence on L is here. L is logarithm. So this coupling are running couplings. They running, what it means running? They change between bandwidths when they're equal to bare values to some other values when they go down to lower energies. The question is how to plot them. Well, trivial to plot them, right? So let's plot them. You get nothing. Because if you start with the fact that this guy was larger than this one, case with repulsion, you end up with repulsion. You cannot just convert water into wine with this. Repulsion stays repulsive. So, in fact, this interaction progressively becomes smaller than this one. So you make situation worse, in fact, by doing this. Seems almost hopeless, but This is the result when I neglected these two guys. Let me now include these two guys. So I go back to these equations, and in fact, you can even analyze this analytically, but the best thing is just to type this in Mathematica, and Mathematica will give you the result instantly, in 1 second. And this is what the result it gives you. It gives you opposite result. I made story a little bit to, in fact, G2 first goes down in reality and then goes up. So I just adjusted parameters such that it goes up right away. I just bare parameters. But this is how it goes. And this is exactly what we want to hear and want to see. Namely, we started with the case when G1 was larger than G2, and it was repulsion, right? But now, look at this. There is a scale beyond which the interaction changes sign and becomes attractive. What means that system itself self-generates scale where it becomes attractive. This is what Kohn-Latinger tells you, but Kohn-Latinger starts here at this scale, right? When we started, we did Kohn-Latinger analysis, we said, let's assume that bare interactions are the same, so you start at this point. Then, of course, we know what happens. This is what RG helps you to do. It tells you that no, even if you start with wrong scenario, I mean that bad case, when initial interaction is repulsive, then basically what you have is interaction come closer to each other and then change sign. Wonderful. If I work at weak coupling, and as long as all this happens, interaction remains weak, I'm on a solid ground. Now the obvious question is why this happens. What happens? Of course, it's the result of interaction with these two guys. And then looking carefully, what you find out is that the reason why this guy is pushed up is because of this interaction, which if you look at the equation, this interaction always grows. It has plus here and plus here, so it definitely goes up with increasing logarithm. This is the interaction which gives rise to spin density wave instability. So the way how to physically read solution of this equation is to say this. We have two pairing interactions. One at small momentum transfer, repulsive. Another at large momentum transfer, also repulsive. The one at small momentum transfer is a bad guy. Nobody wants to help bad guy. So bad guy will go down. But the one at large momentum transfer is a good guy for us. And there is another interaction which comes to rescue, which is the interactions that give rise to magnetism. This interaction grows up, and by growing up, it pushes up good interaction up. So this is intelligent way to say that magnetic fluctuations favor attractive interaction in this particular case in S plus minus channel. If you do the same for cuprates, it will be D wave channel. If you do doped graphene, it will be D plus ID. So this is how interaction eventually goes up. And you can say this in words, or you can say, look, this is the formulas, I present you solution, and this is what comes out. Now, I don't want to make this talk as a talk about iron-based materials. Yes, sorry, yeah. G3 was interaction with, it was basically interaction, let me show you what it was. It's easier to show than to explain. It was interaction at small momentum transfer, but the one that acts in between hole and electron pockets. Total momentum here is exactly the momentum between hole and electron pocket. So momentum, total momentum here is capital Q, the one that separates hole and electron pocket. Transverse momentum is small. This is the interaction which gives rise to magnetism if you look what's going on. Okay, so I want to switch to second part of the talk, and I'm looking at time. I set myself half an hour for one, half an hour for the other. I'm approaching half an hour. So just one phrase about iron-based materials. Of course, if you ask specialists in iron-based whether this scenario is good, they will say, well, this is too trivial. Because what I did, I said that instead of all this complex structure, all this zoo of states with 5 different orbitals, I said just one hole pocket, one electron pocket, which was great because then we can solve everything analytically. In reality, even if we zoom in into what we call low energy, I take a fraction of bandwidth, then it's of course a question of arguing with numbers. This is the bandwidth. So this is what gives you 2, 3 electron volts, or 3, 4 electron volts if you take these distances. What we want to do, of course, to focus on lower energies when all this logarithmical physics takes in here. And it's, of course, always equation for any RG procedure. What you take as the upper cutoff, up to what energy you can keep interaction as k squared over 2m and not include lattice effects. It's a question about numbers. But even if you do this, if you ask what are these Fermi surfaces, now we have 2 hole pockets, this one iron zone, 2 hole pockets at gamma point at 0, 1 hole pocket at pi pi, 2 electron pockets here at this pocket point 0 pi and pi 0, and different colors are different orbitals. So we have 3 orbitals, xz, yz, and xy, that correspond, that give rise to this low energy states. And if you like, and Oscar actually, with Vladimir Svetkovich, really did extremely good work on identifying how to write down. They basically wrote low energy theory for this model. And everyone now, me including, are just taking their model as input and do calculation based on what they did. Anyway, if you take these 3 orbitals and ask how many different couplings you can write down, it's not 5, it's 44. So now you cannot write equations in 5 minutes. But it turns out that you can still write equations. It's ugly procedure, but you do it. Within certain approximation, which for some may be questionable, because you take some of the bands that cross Fermi level but don't include bands that starts some low energies, for example, here, and then, sorry, it should be electron pocket. So you should start with 1 band, say, for example, that this is a Fermi level, that you don't include the band that goes down. Anyway, you can ask the question, what is the leading instability? Now it's a real question about competition. Previously, I was talking only about superconductivity. Now I ask a different question. I put all interaction into play and ask a question. Yeah, we know, we expect that pairing interaction will change from repulsive to attractive, but is this enough? Will it win competition compared to other orders? Because by the end of the day, what I was saying, that this interaction G2 is get pushed by interaction G3, and G3 gives rise to magnetism, to spin density wave. So why not to think about spin density wave instead of superconductivity? It turns out that you have 3 different possibilities. One is superconducting order, another is magnetic order, and the third one is orbital order. You have different orbitals. You can break spontaneously symmetry between different orbitals, which in practice means that there are 2 symmetric orbitals, xz, 2 orbitals which are symmetric under rotation, xz and yz. If you spontaneously break symmetry between the 2, you create what's called orbital order. You can equally well say that you break symmetry within x and y direction. You can call this nematic order. They are all synonymous for the same. So again, to make long story short, what you do, you start by putting all this interaction as a starting point, meaning that I put all couplings into RG procedure. I ask myself how the coupling involve. After I know how the coupling involve, I calculate vortices in different channels, spin density wave, charge density wave, orbital, superconducting, also D wave superconducting, because now everything is angular dependent on the Fermi surface, simply because orbital content of excitation changes along the Fermi surface. And before you will be bored with all this, the real question is, who is going to finish first? And we know what to start with. We know we start with repulsive interaction. And something I'm sure you all know, repulsion is bad for superconductivity, repulsion is bad for charge order, but repulsion is good for what order? For magnetism. Magnetism comes from repulsion. So repulsive interaction, positive G3, give rise to spin density wave because of particular sign changes with spin operators. But which means, for purposes of our talk, that you start with the situation mostly favorable to magnetism. And then the question is, once RG develops, what happens? 2 things happen, in fact. One I discussed, another I didn't. Interaction in superconducting channel changes sign and becomes attractive. It always happens. So push from growing magnetic interaction makes superconducting channel attractive. But less known is that it also makes orbital channel attractive. So there are two channels which become attractive due to push from magnetism. And then, remember, attractive superconducting channel, if left alone, will give you S plus minus superconductivity. Orbital channel, if left alone, will break symmetry between XZ and YZ orbitals. Sometimes it's called breaking of C4 rotational symmetry. Sometimes it's called D-wave nematic order. It's all the same wording. OK, just the result. You calculate susceptibilities in all different channels. And what you need to obtain. It's separate procedure how to calculate the susceptibility, so let's not go into details. The story goes this way. The susceptibility which diverges first is in the channel who wins. If two or more susceptibility diverge at the same time, you look at exponent, and the susceptibility diverging with the highest exponent is also declared a winner. These are three susceptibilities: magnetic superconducting orbital, and you start always with a situation when magnetic susceptibility is the largest. So at the beginning of the story, magnetism is the most favorable. But as RG flows, something interesting happens. Superconducting channel takes over magnetism, and then orbital channel takes over magnetism. Which is interesting on its own, because there is wonderful material, iron selenium, in which the system develops orbital order and then superconductivity, but no magnetism. Magnetism is somewhere here. But also it's interesting on a general term. There is one thing that I probably should mention here, yes, that this is very interesting part of the story, which has physics and also political, social, whatever consequence. You start with magnetic fluctuations that tend to develop magnetic order. And if you forget about everything else, the system will develop magnetic order. But in the process of this interaction is doing good things to other two channels. Good things means that it also makes superconducting channel attractive, it makes orbital channel attractive. Once these two channels become attractive, they become strong competitors. And what these guys do, they conspire and produce strong negative feedback effect on spin density wave channel. And the result of this is this guy that was supposed to diverge first, in fact, will never diverge. It will stay constant. While other channels, the ones that produced by magnetic channels, become divergent. One of them wins, second not win, but it's secondary part of the story. Message here is that basically it's a story that's known to everyone from ancient times, right? Something does good things and create response, and the response kills the source. Examples you can find out in many different fields of science, not science, anywhere. So this is a good example when this happens. So magnetic interaction does two good things. Creates attraction in superconducting and orbital channel. These two bad guys conspire and kill enhancement of magnetic susceptibility. Okay, yeah. No. What you do is this. You do RG in 3 stages, in fact. Let me quickly answer, and then I move to the next part. The RG that I described to you is RG when you write down equation on vertices. So you write down this equation on different G's, you solve them. Then you use this running G's as inputs and create equations for vertex function in different channels. Different channels mean C dagger, C dagger, C dagger. And look how these couplings flow. For this, you use running couplings as input. You solve second set of RG equations. Then you put these couplings into susceptibilities and write third set of RG equations for susceptibilities, although third set is triviality. You just, in fact, calculate susceptibilities. So there's 3 stages formally. Okay. I spoke for half an hour, a little bit more, but now we go to second part. So that part of the story was how logarithm help you to obtain superconductivity. And then superconductivity and other order do something bad to magnetism. Now I want to switch gears and use different approach. It's not entirely orthogonal approach. What I was trying to say is that previous one worked A under assumptions the theory has logarithms. For iron pnictides, yes, is the case if you separate scales, but for cuprates, generally no. There is no such thing as logarithms in different channels unless you are very close to one half point, which not all systems are close. And then you can ask a different question. How can I basically think about the system when I cannot do perturbation theory enhanced by logarithms? Then first thing is to say that we cannot do anything rigorous. This is an important point to understand, that everything I'm telling you right now, starting from this point, is sort of phenomenology. But the idea then is this one, that you look at phase diagram and say, yeah, here more or less I can do perturbation. Here more or less I can do perturbation. But I cannot go in these regions with perturbation theory. But looking at the phase diagram, the player which played important role in this RG physics was magnetism. It is here. Very good. So magnetism is there. You look at iron-based phase diagram, magnetism is there. So then you may say, look, there is a big elephant in the room called magnetism. Why don't we think phenomenological at this stage about a situation when I don't worry why, but what I want to do is to look at the situation when by one reason or the other, the system is approaching ordered state, by which we most of the time think magnetic order. If the system approaches this state, you can say, look, this means that interaction at large momentum transfer almost certainly is enhanced. We know that it enhances this RG, and it's very difficult to imagine that if you have system close to instability at large momentum transfer, that interaction at large momentum transfers will not be enhanced. Then, without even knowing, without really knowing how to prove this accurately, I can make phenomenological assumption that yes, interaction at large momentum transfer is larger than interaction at small momentum transfer. You may say, I lose most interesting part. I didn't prove you how to get superconductivity. It's true. But argument is based now on phenomenology and on experimental facts that magnetism is nearby. Then you can say, look, let's put a dot and go for coffee break. We get attraction with declared attraction. Then obviously what we expect is that somewhere here system will become superconducting because I made the system, I made interaction attractive in particular channel. Being it in cuprates, it's D wave, and pnictides, it's S plus minus, but I made it by hand, using the physics argument. But the story is, now from this point, the story becomes interesting in another aspect. Namely, that the same interaction that is magnetically mediated and this is the ones that give you large G2, also give you other things. It destroys fermionic coherence. Within perturbation theory, of which RG is part of, at least within the one loop RG that we were doing, we didn't touch any effect of fermions. Fermions remains free in what we were doing. Now we want to ask a different question. How the interaction affects fermions? And it turns out that you approach exactly the same point, this one, and if you forget about this, if you just separate between particle-particle and particle-hole channel, you will find that self-energy, which is particle-hole self-energy, becomes singular. The fact that at the critical point, you have self-energy with power smaller than 1, this is canonical definition of non-Fermi liquid. Because if you take any function with power frequency smaller than 1 and ask what's by Kramer's chronic real and imaginary part of this function, they're of the same order. So standard assumption of Fermi liquids that low energy fermions have small damping, parametrically small damping, doesn't work. This is competitor. So now we have another competitor. Previously we have competitor in the form of other order. Here we have competitor in the form of non-Fermi liquid, and why it's competitor? By the way, yeah, if I forget about superconductivity and only focus on this, then you get a picture which you probably saw in a number of books. Subir Sajdev put it, I guess, on on the cover of his book. This is the phase diagram with no superconductivity in it. This is destruction of Fermi liquid close to this critical point. This is because the same interaction, analog of G2, when viewed in a particle Hall channel, give you strong self-energy. If you play the game with logarithms that give you self-energy at higher powers of coupling, so we don't include it into one loop RG, but we're not doing one loop RG, we're just trying to see what we get here. And then we have a story with who is going to have louder voice. Because on one hand, if you ask what this Fermi energy does, you can easily figure out that if you put self-energy with power smaller than 1, it will be parametrically larger than bare omega at small frequencies. And as such, it will kill Cooper logarithm. So you will not get this nice story about BCS-like superconductivity, which happens no matter what. So non-Fermi liquid is bad for superconductivity. On the other hand, if you view it a different way, what superconductivity does to non-Fermi liquid? If the system becomes superconducting, it immediately gaps out low energy excitations, and then you have no phase space for this self-energy. Then you go back, all calculations show that you go back to normal Fermi liquid. So these two effects compete with each other. Non-Fermi liquid is against superconductivity, superconductivity is against non-Fermi liquid. And this is a separate interesting problem, of which again we phenomenologically assume that yes, there is strong interaction that give rise to attraction. But the price we have to pay is that the same interaction gives rise to non-Fermi liquid, and the two effects compete with each other. What's another, yeah, sorry.
So does this mean when superconductivity doesn't completely gap the Fermi surface between these two can coexist?
Ah, good question. I was thinking about talking about this, but I thought that it will take a lot of time. So the short answer is no. Even if you have D-wave superconductivity and you have nodes, and you calculate what the imaginary part of self-energy is, it will go as omega cube. So it will still be small compared to bare omega. So you will not be able to restore non-Fermi liquid even with superconducting state with nodes in the gap. Part of the story that is important here, and again was not present in our G analysis when we consider G1 and G2 as just constant interaction, is the fact that if you look carefully what's going on, bosonic dynamics becomes important. What it means, the word bosonic dynamics? It means that interaction cannot be treated as a constant because the process which we don't include in RG, the process of decay of interaction in a particle Hall channel or bosonic response in a particle Hall channel becomes relevant process. And again, to make long story short, it basically tells you that when you deal with effective interaction that give rise to attraction and to non-Fermi liquid, have to treat this interaction dynamically. And for most of the cases, this interaction is overdamped because any bosonic response can decay in a particle Hall channel, in a particle Hall pair, and give energy to particle Hall pair. This was called Landau damping. If bosons, and now then you ask a question, you have bosons, dynamical bosons, you have dynamical fermions. Boson is what mediates interaction between fermions. It's what originally we have as dashed line, we call it G1 or G2. Now it's really dynamical boson which accounts for the closeness to magnetic instability or some other instability in a particle Hall channel. And when you look into this, it turns out that there is one limit, or one set of models, better say, not limit, set of models. When a person called Eliashberg, by the name Eliashberg, told us how to do calculations. This is a case when bosons are slow mode compared to fermions. And basic message here is this, that all momentum integration with proper symmetry of the superconducting state, etc., they all can be done exactly. But what you need to solve is the equation for frequency dependence on the self-energy and frequency dependence of this guy called pairing vortex. This is the guy when it develops non-zero value by itself, give rise to superconductivity. There are two objects. One knows about superconductivity, another about non-Fermi liquid. Both guys generally depend on momentum and frequency. And again, there is a limit when all momentum dependence can be taken care of accurately. You end up with these two guys, and these two guys interact with each other. Sorry, interact with each other is not the right word. These two guys are coupled to each other. Namely, there is equation for the self-energy, which knows about pairing vertex. There is equation for the pairing vertex, which knows about self-energy. Notice that self-energy comes into denominator of equation for the pairing vertex. Pairing vertex comes into denominator and equation for the self-energy, which is the simplest way to say that they compete with each other. So when one becomes large, you try to minimize or diminish the effect of the other. So what we have to do is to analyze the set of these two equations. Where is the interesting physics? Here. They both contain, sorry, first of all, yeah, superconducting gap. When people talk about superconductivity, they normally say superconducting gap, gap equation. Superconducting gap is proportional to this guy, but with the prefactor which knows about the ratio of frequency and frequency plus self-energy. All frequency here are Matsubara frequencies. So basically it means that if you know phi, you know delta, and that's almost equivalent numbers. It's just easier to write equation on the vertex than on delta. So to continue with the phrase I've started, this is interesting object. This is what this boson tells you. And if you are at the critical point, at the point where the system is about to develop magnetic order, or again, some other order, it turns out that this guy is a singular function of frequency. In a Fermi, you can ask, what about Fermi liquid? In a Fermi liquid, we know what's going on. This guy is a constant. If this guy is a constant, this equation gives you self-energy, which is completely regular, Fermi liquid-like. This gives you BCS pairing problem, which means that if this guy is, for this notation, positive, read attractive, then you get solution of the gap equation, which will be BCS gap equation. So story here is this. If chi is a constant, it's BCS. Original Eliashberg story is the story when this chi is constant at small frequencies and then dies off as 1 over omega squared at large frequencies. Then you don't need to worry about upper cutoff and the integrations, and everything is done, and it's called Eliashberg theory of superconductivity, which is not qualitatively different from BCS. It just allows you to do more rigorous calculations than in BCS. But in our case, in a quantum critical point, where we ask about competition between non-Fermi liquid and superconductivity, situation is qualitatively different. Because this interaction, this chi, becomes singular function of frequency. You forget about superconductivity, you put this chi into this equation, you get self-energy that goes as omega to power of 1 minus gamma. That's exactly what I told you before, non-Fermi liquid. You put this into pairing equation, you get something that you need to solve, because it's now non-trivial integral equation for the pairing vertex. And one quick thing before I show you the results, notice that I specifically put letter G here to make this guy dimensionless, and if you look carefully at this equation, everything else is dimensionless. Pi t, t is temperature, pi is 3.14. Compensate denominator. So everything is dimensionless here, meaning that this letter G sets the only scale in the problem. What it means physically? Physically, it means that if you, oh, sorry, I'm running a little bit ahead of myself. Let me first tell you about examples. My apologies, I forgot that I have to tell you this. Examples. Well, there are 3 known examples, mostly known examples. One is what happens near a nematic transition, or near a situation when fermions are interacting by exchanging gauge field. Nick was, I guess, number 1 of looking into this problem. This is what called, which is the problem which has exponent 1/3. Let's skip details. You just take particular form of interaction integrated over Fermi surface, put mass to 0, which means that you are in a critical point, you get exponent 1/3. If you are close to antiferromagnetic point, you get exponent 1/2, and again, list of people who are studying this is pretty large. The same happens if you are close to charge density wave critical point. Our high energy colleagues, most of our high energy colleagues and some of our condensed matter colleagues, focused very much on the case near 3 dimensions when you can expand in gamma. This is small gamma. When the system is almost in the Fermi liquid regime, but a little bit off. Then you can do perturbative expansion in gamma, and this is a different story. But I just want to show you that there are examples, known examples, for this different exponent gamma. For us, it's important that gamma is larger than 0. We deal with non-Fermi liquid as a critical point. So now back to scales. I want to tell you something very simple, that there is only one scale, letter G. What it means? It means that when I solve for the pairing, Tc by definition is equal to this overall scale G times some function of exponent gamma, but can be 0. It can be that non-Fermi liquid completely kills superconductivity. We'll see whether this is the case or not. But anyway, there is no other letter. It's just letter G. So overall scale for Tc is set by letter G. What about self-energy? What about non-Fermi liquid? You need, if you put self-energy like fractional power, you need to add something with dimension G in order to make total dimension equal, the same as frequency. What is the scale? You look at calculations, you put in interaction, calculate self-energy. You find that up to prefactors, this scale is again G. What else you expect? There's only one scale in the problem. Look at this, and then you find out that basically with this form of self-energy, physically system or frequency range is divided into what's called quantum critical regime, the regime in which self-energy is larger than the bare frequency. This is where fermions are incoherent. And the regime of high frequencies, when you just go to large frequencies and omega is larger than self-energy. This is where fermions are pretty much like free particles. This is called upper boundary for non-Fermi liquid behavior and is set by the same letter G. So basically, non-Fermi liquid and superconductivity, they fight for the same range of frequencies. So this is real competition between the two effects. Very good. But this also creates a problem for theorists. Because if you have two phenomena, and two phenomena are defined on the same scale, then one thing is to ask, of course, powerful computers to help you, which is a completely legitimate way. But if you want to do something analytically, then it's a bad case, because you cannot play any games. You just have one letter, you basically scale it out. You have, on one hand, universal problem, but the second question, what to do with universal problem. You don't have any expansion parameter to deal with. And as such, theorists try to invent parameter, which you can manipulate and try to find out the real interplay between non-Fermi liquid and superconductivity. So the goal is now, in the next slide, is to say, let's invent parameters. And by varying this parameter, we either definitely make tendency to superconductivity larger, or definitely make tendency to non-Fermi liquid larger. So how this is done, the easiest way is just by hand. Just put factor of n here in the pairing channel without even thinking more. Then if n is large, you make superconducting channel bad, right? You decrease interaction in this channel. When n is small, you make this interaction large. Sorry, when n is large, you make this interaction small. When n is small, you make this interaction large, right? So by varying n, you basically vary relation between interaction in two channels. So the goal is to split the two interactions. You can also do it a little bit more accurately by considering difference between, say, in cuprates, D-wave interaction, which is present here, and S-wave interaction, which is present here. But the result is the same. You need one parameter to manipulate the ratio of two interactions. For high energy oriented people, you can do this by extending theory to SUN. If you want to take n as a large parameter, you can just rigorously do it by doing SUN global symmetry. But for us, it's just n is a parameter. I want to find out what is the interplay. And with this, basically, what you expect. I'm running almost out of time, so I will tell you a simple thing and then quickly tell you about non-trivial thing. So what do you expect generally? Two channels compete with each other. They're both of the same order, right? And I put this parameter n. When n is large, superconductivity is weakened. What do you expect? Non-Fermi liquid will win, right? When n is small, superconductivity will win. Well, let's go to 0 temperature and do analytical calculations. This is where I would be happy to give you 3 lectures on this, how to convert integral equation into differential equation, solve them with boundary condition, and then find out how to connect solutions in different regions. This is the beauty of doing analytics, but here is the result. Of course, you are all right. Of course, there exists critical value of n, which separates. Large n means I reduce pairing interaction. It turns out that yes, if n is large enough, then non-Fermi liquid wins over superconductivity. At 0 temperature, you do get normal state, which is non-Fermi liquid normal state, but this is normal state. So it turns out, despite attraction, which we put by hand, system cannot be superconductor because incoherence wins. And incoherence kills superconductivity, not competing order, incoherence. If n is smaller, other way around, superconductivity wins. Expected result. Nice thing is that you can write down n critical in terms of gamma functions and, as I said, solve this problem accurately, but here is the result. Let's add temperature axis and see what's going on. Well, this is what you expect. And this is what comes out if you start with 0 temperature and then do standard analysis by basically by identifying relevant frequency scale and associating it with temperature. Then you expect this is your superconducting region, this is your normal state. In some sense, this is the answer, in some sense. So if you ask rigorous answer, what are phase transitions in the problem? Here is the answer. We can stop here and go to coffee break. But of course, there's interesting caveat of the story. Namely that it turns out that if you look and actually solve the problem, it turns out that there is another range, and it's pretty wide range, where the system shows pseudo-gap behavior. And you may say, well, interesting, pseudo-gap is something resembles cuprates, of course, but the question is why? One is to say it happens this way, but here there is a practical reason why this happens. Let me name the reason, and then I probably stop them. So there is a particular reason why in this situation, when all phase diagram is due to competition between non-Fermi liquid and tendency to pairing, there is a wide range of temperature. And see, I even put numbers here, so we know how to calculate this line. So why? It turns out that pseudo-gap is in the equations. We just need to extract it from there. And the way how we do it is this. We look at this Eli-Ashberg equations. This is what I used to obtain 0 temperature result when I treated frequencies as continuous variables. Remember, Matsubara frequencies are discrete at finite temperature and continuous at 0 temperature. So at 0 temperature, this is what gave me this critical value of n. And what I used the fact that self-energy was non-Fermi liquid. This is what gave me competition, right? This is how I get physically critical n. Either one effect or other wins. But this guy with magnifying glass is looking now more carefully and find out interesting that if you solve this equation and you find out that there are 2 Matsubara frequencies, pi t and minus pi t, for which self-energy vanishes. At 0 temperature, say, I don't care. These are just 2 points out of infinity. But at finite temperature, I have discrete points. So I have 2 discrete points, if you like, n points in the set of frequencies for which self-energy vanishes. And then it's interesting. So previously I said non-Fermi liquid. Now there are 2 Matsubara frequencies for which there is no non-Fermi liquid because there is no self-energy. There's only bare omega there. And then I look at solution of this equation. This is equation, linearized equation. So I ask equation about instability. And I solve it, take large n limit just to be on a safe grounds. And it turns out that there are 2 frequencies which are not affected by this large self-energy, but the fermions as these 2 frequencies interact with each other. And to make long story short, what it gives you, formally solving this equation, I get a temperature which never goes to 0 for any n, no matter how small, how large n is. Which means that for system has enormously large self-energy compared, so enormously large interaction in the particle Hall channel, very large self-energy for all frequencies except for 2. And for these 2 remaining, There is no self-energy. I solve for the pairing. I get this temperature. And this precisely what gives me this temperature, which splits this range into a range where I do mean field calculations. And in the mean field calculations, what I get pairing, but it's now induced by this Matsubara frequency. This acts as a source for the pairing. While here, everything is fine. All frequencies are equal. Let me finish with one phrase. This is mean field analysis. Eli-Ashberg theory is mean field theory. Let's follow Nandini, who gave wonderful talk yesterday, and go beyond mean field and calculate stiffness. Because we know that we need superconducting order. Order means that the phase of the order parameter needs to be fixed. This is determined by the value of the stiffness. And this will be my last slide. Look at the stiffness here. These are real calculations. Stiffness is smaller, parametrically smaller than temperature. This is a situation when phase fluctuations are crazy. They're enormous. While I calculate stiffness in this region, I get Fermi energy, which means the stiffness is very large. The bottom line is that this range, where there is a specific reason for pairing, is a range when there is a very small, parametrically small stiffness. This is a range where I have large stiffness. Then you follow standard procedure how to calculate TC based on stiffness, you get this line. So this is how you get phase diagram. As any theorist, I want to finish saying, well, great, I got it. And now I want to show you a bunch of experimental data, a bunch of theory calculations of density of states, of spectral function. They all agree with Cuprates, because every theorist must finish a talk by saying, my theory agrees with Cuprates perfectly well. But there is no time for this, so I'll stop here and tell you that, yes, my theory agrees with Cuprates perfectly well. If you want to see it, ask me. I will show you the data. OK. Let me put conclusions here. There is a push from developing fluctuations in spin density wave channel, which allows system to develop attraction in a pairing channel. There is a feedback from this attraction of killing the source. And for the second part, basic message that we have superconductivity competing with non-Fermi liquids. This was the main message here. The rest are details. This competition can be treated more or less rigorously at zero temperature. But nice part of the story is that for this particular reason why superconductivity sometimes appears, sometimes does not appear, competition between superconductivity and non-Fermi liquid, there is a specific reason for pseudo-gap. And in this pseudo-gap, there is only one scale in the problem, is set by temperature, and everything is scaling function of frequency over temperature. So basically, and yes, I said that every theorist has to finish with this phrase.